Good afternoon, everyone, and welcome back to another DIR 2020 Lightning Talk session. I have the incredible Christine Bauer with me here. She will be our session chair, and without further ado, I'm just going to pass on word to her. So, Cristina, the floor is yours.
Thank you. It's really great that I can chair this session today on fairness and related topics. We have 4 great presentations. I look forward to them. And the first one is presented by Anca Dumitrache. The title is called Beyond Optimizing for Clicks, Incorporating Editorial Values in News Recommendation. You can see her already on the screen, and I say the floor is yours. And for all others, use the comments, and so we have the discussion afterwards, and I will pick those discussions up. So don't forget already forming your questions during the talk. Anca, please go ahead. Thank you.
Hi, everyone. Thank you, Cristina. So even though you see kind of different affiliations to all of my co-authors here, actually this work was done when we were all working together at the FD Media Group, and we were actually part of quite a large data science team. And I'm happy that I saw a couple of familiar faces already from this team in the YouTube chat. So hopefully we can all talk to you about this later in Gathertown. For those of you that don't know Financieel Dagblad, it's a daily Dutch newspaper that is focused on business and financial news. And our goal with this project was to build a system that can give personalized article recommendations to our readers, while also upholding editorial values for providers. And to do this, we looked at 2 research questions. So first, we wanted to investigate whether the recommender system that we built is able to provide useful recommendations. And secondly, we wanted to know whether we can steer the behavior of the users towards more dynamic reading without losing the accuracy and the usefulness. So the recommender system that we built is starting from implicit feedback data. So the data that we collect is from readers logging into the website and reading articles, clicking on articles. So this is the positive data, and the negative data is the articles that they have seen on the website but have not clicked. And as you can imagine, this is quite a biased sample towards the negative articles. So most readers read just a handful of articles every day. The majority of the articles do not get read by one single user. So we had to do also some negative sampling in order to balance the training data somewhat. And because this is continuous cold start problem, we had to focus mostly on content features, right? So the articles, they are newly published every day, and we want to recommend the new published articles, not the historical articles. So because of this, we cannot rely we cannot do collaborative filtering. So we have to use content features for our recommendations. And we have a very big feature space that you can read about in the paper, as well as our supplementary material. I think it was like around 15,000 units in one feature vector for one user, so that's quite a lot. And the model that we use to train is a gradient boosted decision tree model that was trained on historical data from the past, I believe, a week or so for one user. And then this was able to generate a list of recommended articles for each user, a ranked list of recommended articles. As I mentioned before, so we looked at content features to generate these recommendations. We try to steer away from using demographic features for the recommender. Instead, we focused on reading behavior of the user, aggregated reading behavior, article language features such as metadata, as well as some enrichments, some of which we calculated ourselves, like automated tagging, word embeddings, and things like that. And we also look at the user article features, which represent the overlap between the article feature and the average user behavior. So like I said, you can read the detail of these features in the paper. It's quite a lot of them. But next to the user focused analysis, we also performed a second analysis from the perspective of the stakeholders, in which case it is the journalists. So together with Bastian Helberger and also inside the community of FD, we performed several meetings with journalists, data scientists, developers, and we also did a deep dive in the literature, and we were able to come up with these following values that the editors of the newspaper found to be very important when recommending news. So first of all is that we want to be able to surprise readers with the recommendations, so we have serendipity. Secondly, we have dynamism, that the news is timely and fresh. Next is the diversity of the news recommendation. And finally is the coverage. So we want to have as many articles as possible. So these are the values that we also want to incorporate into our success metrics next to the usefulness of the recommendations. So in our first experiment, looking at whether or not we can provide these useful recommendations, we did an offline study. We compare our recommender system with the baseline of a statically curated list of 5 articles that is manually edited by editors. And we present our recommendations to users in 3 ways. So we have a widget that recommends the top 5 recommended articles published in the last 24 hours. We have a list of recommended articles from the last 7 days, and then we have a separate page for all the articles in a recommender. We did the study over 1 month, and we looked at about 100 power users. This is how the recommendations look like on the website. Next, we also propose a couple of metrics. So for the accuracy, we have the classic information retrieval metrics, NDCG, precision recall. For diversity, we investigate intra-list diversity, which is a metric that takes into account a similarity between items in a list, and the similarity can be calculated based on various aspects, such as authors, tags, word embeddings. For dynamism, we looked at the interlist diversity, so how the list changes from one time step to another. For serendipity, we looked at the articles' dissimilarity to the aggregated history of the user. So we want to, in order to surprise the user, we want to recommend articles that are as different to their reading history as possible. And finally, for coverage, we look at the percentage of daily published articles that are served in a list. So I'll just go very quickly through these results. You can find more details in the paper. For accuracy, what we found is that, yes, the recommendations, they are at an acceptable level. For diversity, we have seen that the recommendations from the recommender system are more diverse on topic and content, but less diverse on authors. And they are both quite diverse on tags. So the tag diversity comes from the fact that we actually have a very big tag space for each article. So this doesn't surprise us. And the lack of diversity on the author side. So what happens with is that authors are actually a very important feature for recommendations in our model. So our recommender is actually narrowing down a little bit on authors that the reader prefers, as opposed to recommending a more diverse set. When we look at dynamism, we notice that while the recommender system list doesn't change very frequently, once it does introduce new items into the list, and hence they are more dynamic than the static recommendations from the editors. For the serendipity, we have seen that the manual rankings, they yield more, they have more serendipity than the recommender system. For the tags and the authors, but for the content, it is the recommender that is more serendipitous. So I don't have a lot of time left. There are a couple of more results that I wanted to show you. For the coverage, we see that the recommender system has slightly more coverage across all the users. We also had a second study where we actually tried to bias the reading behavior towards reading articles that have more dynamism. And our basic idea was just to rank newly published articles higher. What we saw is that actually the accuracy, when we bias the recommendations with dynamism, So the accuracy is sort of equal to our baseline, where we don't bias these recommendations in the online experiment. Whereas the dynamism, but also the serendipity and the diversity across in the dynamism treatment increased in comparison to our baseline. Overall, we see an increase in all of these usefulness values that our editors want to see in the recommendations by using this very simple linear re-ranking of the recommendation using the dynamism. There's a couple of limitations to the study, mostly to do with the implicit feedback and presentation bias. There were some interference from other A/B tests in the online experiment. But overall, what we saw is that the news recommendation can benefit both the news providers and the readers, and that while we can increase the overall item coverage for the provider, we can also provide more dynamic and surprising content recommendation and increase diversity of news consumption. And that algorithm design with multiple stakeholders doesn't need to be a trade-off, that we can actually satisfy multiple values at the same time. So thank you for your attention, and looking forward to your questions.
Thank you, Anca. You can just hear me clapping. There are already a couple of questions out there, so I just pick some out. The first question is, Lucas is saying, thanks for the great talk. Regarding negative sampling, how did you sample from the negative items? Did you find strategies that worked or didn't work well in practice? Do you have some insights on that?
Yeah, so I have to say, we didn't do too much experimentation here. I believe we just did simple random sampling. The idea was to eventually build up to doing like popularity-based negative sampling, so that we can remove the popularity bias from the data, but we didn't experiment with it in the end. No.
Okay. And right away, second question from the same person: what similarity function did you use for the intralist diversity?
So we looked at, so for the word embeddings, we looked at cosine similarity. For the set-based metrics, so like tag diversity and author diversity, there I believe we used, it wasn't the Gini coefficient, I think it was the Shannon entropy, I want to say. Let me check very quickly in the paper. So it was, the Jacquard index, sorry about that. Yeah. So these two metrics, depending on what type of input we have for the data.
Did you experiment on this one, or you've?
So actually, we did experiment with the Gini coefficient, with Shannon entropy as well, and we found that for the diversity they were correlated. The results were more or less the same. I think for the serendipity, the Gini was preferred just because there was a big set imbalance between the user representation, so they have much more tags and authors than the article representation, which had like a bit smaller set.
Okay, and another question. So many questions. Were the insights on how more diversity interacted with accuracy? Did they work together, or were they like related, or did they oppose to each other? Do you recall that?
Yeah, so because we didn't do an intervention study with diversity, we couldn't check this in an online study. But what we saw from the offline experiment is that we could increase the diversity, at least for the content and for the content-based metrics, so for the word embeddings and for the section, as well as the tags, while not losing too much on that. But yeah, this is a caveat because it was an offline study. There is always a bit of a difference when moving online.
Okay, and finally, a personal question of personal interest. So you integrated the values, the editorial values based on research, and I would be very interested to know whether there is something out there, what journalists think concerning fairness, how they want to be represented or not in these recommendations, because I found as a result in your experiments that there was not so much diversity among the authors. Was this mentioned somehow in that it should be more diverse, or there's just no reaction on that? Do you know anything?
Yeah, so this is something that is definitely important to them, for sure. That's why, yeah, it came up also even before the experiments that, yeah, they want to see diversity of authors as expressed in the recommender system. So our hope is that we would eventually be able to bias the rankings in the same manner, like we did with the dynamism, to also increase the diversity. So yeah, this is quite important indeed.
Yeah, so maybe something that we can hear about next year, how to improve that. So thanks for your talk. Thanks for all the questions on this talk. Thank you again.
Thank you.
And we move to the next talk. It's given by Masoud Mansoury. The title of the paper that he presents today is FairMatch, a graph-based approach for improving aggregate diversity in recommender systems. Again, a reminder, use the comments so I can pick up your questions and ask those to Masoud afterwards. And I say the floor is yours, Masoud.
Thank you. Hello, everyone. My name is Masoud Mansoury. I'm a PhD student at Eindhoven University of Technology. The paper that I want to present is FairMatch, a graph-based approach for improving aggregate diversity in recommender systems. This is a joint work with my colleagues from TU Eindhoven, DePaul University, and University of Colorado Boulder. Fairness is the topic that recently received attention from researchers, and it has been shown that it is the key element of success in any recommendation-based systems. But these systems suffer from popularity bias, where few popular items are frequently recommended, but majority of unpopular items do not get their deserved attention. So popularity bias has causes several issues. One of them is low coverage of the recommendations, and also it causes unfair distribution of recommended items. So in this paper, we tackle unfair distribution of recommended items by improving recommendation diversity. In the literature, there are two notions of recommendation diversity. First is individualist diversity, which refers how diverse the list of recommendation is for each user. Another one is aggregate diversity, which refers how diverse the list of recommendations are for all users. But high individualist diversity does not necessarily imply high aggregate diversity. For example, assume that you have a system that recommends 5 different items to each user. So in this situation, you will have high individualist diversity because each user received 5 different items. But overall, you have low aggregate diversity from this recommender system because you just recommended 5 items among many items in the system to everyone. So there are several problems with the system with low aggregate diversity. First, it only concentrates on a few popular items, which may negatively affect users' experience in terms of item discovery in the long run. And also another issue is that it causes unfair distribution of items from the supplier's perspective, because only few popular items from some popular suppliers are frequently recommended and other suppliers are ignored. So in this paper, we address this problem and aim at improving the aggregate diversity of recommender systems. The idea in this paper is that we introduce FairMatch algorithm, which is a graph-based algorithm that works as a post-processing approach after recommendation generation for improving the aggregate diversity. The goal of our algorithm is to improve the visibility of high-quality items that have low visibility. For example, assume that this is the long recommendation list of size 4 for user U1, and this column here shows the visibility of each recommended item in the long recommendation list. For example, here 70 shows that means that item I2 is recommended to 70 users in the long recommendation list. And the goal is to generate final recommendation list of size 2 for each user. As you can see in this example, here we have item I3 that has the lowest visibility in the recommendation list. And also this item is not also shown to the user U1, although this item is also relevant to user U1. So the goal of our algorithm is to find items like I3 and then promote them to be shown in the final recommendation list. We do this by iteratively solving maximum flow problem on recommendation bipartite graph. This diagram shows the process of our FairMatch algorithm, which has 4 steps. So in the following slides, I will explain each step one by one. So the first step is graph preparation. In this step, given long recommendation list, we create recommendation bipartite graph as shown here as an example. The left nodes are the recommended items, the right nodes are the users, and edges between left and right nodes are the recommendations. And also for the purpose of our algorithm, we also add 2 special nodes, S1 and S2, and we connect S1 to all left nodes, and also we connect all right nodes to the S2 node. The second step is weight computation. In this step, we just compute the weight for all edges on the graph. For edges between left and right nodes, we define the weights as the weighted sum of item visibility and relevance. So here is the equation that we use for computing weights between left and right nodes. Here we have 2 parameters. Degree I is the visibility of item I in the graph, which is the number of edges going out from node I to the right nodes, to the user's node. And rank IU is the relevance of item I for user U, which is the position of item I in the sorted list of recommendation list for user U. So based on this definition, lower rank means more relevance, because, for example, if you have sorted list of recommendation for each user, item in the first rank, in the rank 1 would be the most relevant item for that user. And alpha is a hyperparameter to control the trade-off between accuracy and diversity. Also for weights for edges connected to S1 and S2, we just equally distribute the total capacity of left and right nodes to those edges. But for detail about those computation, you can check the paper. And the third step is candidate selection, which is identifying high-quality items that have low visibility. We do this by solving maximum flow on the graph that we prepared in previous step. There are several algorithms for solving maximum flow problem. In this paper, we use push relabel algorithm, which it provides us some functionalities that in our algorithm, we use those functionalities from this algorithm. So after applying push relabel algorithm, it returns left nodes that are connected to the edges with low weight. So those nodes that are connected to the edges with low weight will be the items that we desire to find. Those are the items that are high quality, that have low visibility. But let's look at the weighting computation equation again. We have 2 parameters. As I said, if we have so the nodes that are connected to edges with low weight, this W would be low value. This W would be low when we have low value for degree, which means low visibility, and we have low value for rank, which means more relevance. So in this situation, we will have low weight for those edges, and nodes connected to those edges would be the items that are high quality and have low visibility. And we want to promote them to be shown in the final recommendation list. And in the last step, which is constructing the recommendation list, we just combine the original recommendation list, original top-end recommendation list generated by a base recommender with the identified items in the previous step. For example, here we just found I3 as the item that need to be promoted, and also this is the original top-end recommendation list. We just combine them together by replacing the item in the original list that have the highest visibility with the item that we found in previous step. So for experiments, we use 2 data sets, opinions and movie lens data set, and long recommendation lists are generated by 2 base recommenders with different sizes, 20, 50, and 100, and also the final recommendation size is 10. So these are the baselines that we used for our for comparison. And So this table shows the results on opinions dataset for recommendation list of size 50. So we just picked the results that have almost the same precision value, except for random and reverse, which are two naive algorithms. As you can see, with the same precision value, our FairMatch algorithm has the highest and significant aggregate diversity. And also in terms of fair distribution, we use two metrics, entropy and Gini index. As you can see, we also have better, fairer distribution into using FairMatch algorithm, but the improvements are not significant. And also we also observe the same pattern in terms of long tail coverage for FairMatch algorithm. So in conclusion, we propose a graph-based approach for improving aggregate diversity of recommendations. Experimental results on two data sets showed that our FairMatch algorithm can improve the aggregate diversity compared to other baselines. Thank you.
Thank you, Masoud, for this great talk. And you stayed almost in time. That's great. I can see already a question there, so we'll read it to you. How would you deal with item cold start? Would new items be overexposed because of the low or even zero valued start visibility? So
yeah,
the cold start situation.
Yeah, actually, one of the slides that I showed you, the bar charts were for long tail coverage, that we showed that our FairMatch algorithm is able to improve long tail coverage of recommendation. Those long tail coverage are the items that, for example, are not popular. So there is not much rating about those items. But if you mean by new items, the items that we do not have any rating about them, our algorithm would not work for them because we do not use any content information. So we just tested our algorithm on long tail coverage, which we can consider as cold start items.
Okay. A personal question. So you looked on the items perspective to reach coverage and diversity in there to be fair in the end. Did you also have a look at or consider that that behind each item is a specific provider, so item provider, and typically, depending on the domain, one item provider can have several items, and one item provider can have 10 items and another item provider just 2. Did you consider that in your work, or is this something where you decided, no, we don't look at this at the moment because it's too complex?
That's a very good question, actually. Yeah, actually, this is one of our future work that we mentioned in our paper, and also we just extended the version of this paper, and also our current work, which we consider suppliers as well, as you mentioned, is under review in a journal, and also. So yeah, we just so in this version that we published in UMAP 2020, we did not consider in the supplier information, but we extended this paper and we considered the supplier as well.
Okay, then let's hope that the reviews go well and that we can soon read the results and you can present it next year.
Yes,
I don't see any other questions, but something I'm interested in, maybe I didn't get it in the presentation, because you speak of like items with little visibility, no visibility, but you also speak of high quality items. When you consider different domains, how should we decide what is a high quality item based on that there is no visibility? Did we have any considerations on that?
Yeah, actually, in this work, we considered the quality of items based on the score that is predicted by the base recommender. So we have a long recommendation list, and for each recommended items, we have a score that is predicted by base recommender. So we just consider that score as a quality. Maybe, for example, if we do not use a good base recommender, maybe we do not have a, for example, good estimation of the quality of items, but we just stick with that. We just trust the base recommender for the quality of recommended items.
Okay, yeah, that's good. I just recently had a discussion with someone. Well, do all long tail items like deserve to be visible? That's a very, very big ethical question as well. So I thought I want lots of information from everywhere too, that we can also solve that.
Yeah, in this work we just try to, for example, provide the equal visibility for all the items. Another definition for fairness that we did not consider in this work is, for example, you consider proportional fairness. That, for example, how, for example, the item, for example, so how many times each item should be recommended is dependent to its, for example, merit from the rating data. So we did not consider that one in this work, but it is another type of definition for fairness we can consider. Yeah.
Okay, cool. Thanks for your talk. Thanks for all these answers. Again, clapping. You only hear my clapping, but I'm sure a lot of people are clapping already. And we move on to the next speaker. I'm looking forward to this talk by Tintarev. He will talk about a paper that is called Assessing Viewpoint Diversity in Search Results Using Ranking Fairness Metrics. Again, don't forget to post your questions and comments in the comment options, and I will pick up your questions. And I give the floor to Tim.
Thank you, Cristina. So hey everyone, my name is Tim Dravs, and this is joint work with Nava, Tintarev, Ujwal, Gadiraju, Alessandro, Bozzon, and Benjamin Timmermans. And I want to start with a little anecdote, because a while ago I was in a discussion with friends about veganism, and while everyone was discussing on both sides of this issue, I thought that I myself don't really have any educated opinion on that topic whatsoever. So what I did is, as soon as I got home, I conducted a Google search, and here you can see a screenshot of that. The query here was, should I be vegan? And if you zoom in a little bit to the individual search results, you can see that the first 5 of these top 7 that are depicted here say essentially, yes, you should be vegan. And only results number 6 and 7 say, no, you should not be vegan. The problem with search result rankings like that is that research has found that when there's not a viewpoint diversity really across a search result ranking, this can really influence the attitudes of users who don't have a pre-existing opinion on the topic. This has been dubbed the search engine manipulation effect before. It's quite a contentious term, of course, and it's not to assume some malicious intent on the side of the search engine, but simply describes that, for example, in one study, they were able to manipulate the voting preferences of previously undecided voters into one or the other candidate simply by rearranging the same set of search results that were shown to participants in this study. So clearly there's an issue that has to be dealt with. But in order to move towards solutions here, we of course have to have some way of measuring this viewpoint diversity and actually have a quantification. Of course, we have some subjective idea of how a list could be more or less viewpoint diverse across the ranking, but what is needed is really a quantification. And that was the core idea behind this paper, because currently such a measure does not exist. And as we started this work, we looked a little bit at metrics and methods that perform similar tasks. And one group of metrics that was really interesting here was the group of ranking fairness metrics. I think we will hear more about this later today in the keynote, but just to give you a quick idea of what these metrics typically do. So imagine you have a list of job candidates and you are concerned that female job candidates might not get a fair coverage across the ranking. Then you can define female as the protected attribute and apply one of these metrics to see whether female job candidates are treated fairly across the ranking. And that is really what's important here, and what's also the distinction between fair ranking and regular fair machine learning, is that we don't just worry about the proportion overall of female candidates, but we really want to have this proportion displayed across the ranking. So in our paper, we asked, can we use these ranking fairness metrics to somehow assess viewpoint diversity in search results, which is related, but not exactly the same thing, of course. And what we did is we defined two different notions of viewpoint diversity, that's two different definitions that a ranking assessor might have when looking for viewpoint diversity in a search result list. And then we conducted two different simulation studies to evaluate several existing metrics, but also evaluate one novel metric that we, in fact, proposed in our paper. And before getting into this, we, of course, had to decide on some set of labels that we can assign to documents that represents the viewpoint that this each document expresses with respect to some debated topic. And I'm going to illustrate this again at the veganism example. So if you imagine a scale from completely strongly opposing veganism to strongly supporting it, then essentially what we did is we separated that scale into 7 different categories. It's kind of an ordinal scale from extremely opposing to extremely supporting, with also a neutral category in the middle for documents that don't have any conclusive viewpoint on the topic. And then, for example, if you have a search result item like this, why we shouldn't all be vegan, that is something that could fit in the somewhat opposing category, whereas this article here from PETA.org might fit better in the extremely supporting category. And then based on this taxonomy, we thought, okay, what now could be the goal of a ranking assessor when they want to assess for viewpoint diversity? And the first aim that we thought of was a situation where we are concerned about a particular viewpoint or a particular group of viewpoints. In this example, we might be concerned that the opposing side of an issue is not heard enough, or at least we want to make sure that this opposing side gets a fair coverage throughout the ranking. So we define this group of viewpoints as the protected viewpoint, so to say, and everything else as the non-protected viewpoints. And this is what we refer to in the paper as binomial viewpoint fairness, but it's essentially the same, the typical fair ranking case, similar to what I explained earlier with the female and non-female job candidates. And then another ranking, another viewpoint diversity scenario is, of course, when you sort of want to protect all viewpoints at the same time. So you're not concerned about one viewpoint in particular, but you want to see that all viewpoints get a fair coverage across the ranking. And this is what we refer to in the paper as multinomial viewpoint fairness. And then what we did is we conducted 2 different simulation studies on 3 different synthetic data sets that we created. These data sets simulated basically lists of documents that had viewpoints labels, and they only differed in the distribution of viewpoint labels. And then per set, we created rankings to simulate different levels of viewpoint diversity or ranking bias. And then we computed the metrics we tested on each simulated ranking. Here, I don't have time, of course, to go into each metric that we test. Instead, I'm just going to talk a little bit about the general results, what we found in the high-level takeaways. So this is an example of one metric called NDD that we tested. On the x-axis, you can see a ranking bias as performed by our simulation. So when ranking bias is -1, then the protected viewpoint is extremely advantaged in the ranking. If ranking bias is 1, it's extremely disadvantaged. And what we can see here is that generally the metric works. So it has it outputs low values for low levels of ranking bias. It outputs high values for high levels of ranking bias. But we can also see that it's asymmetric. So in fact, as the proportion of protected viewpoints decreases in the overall data set, the metric outcome decreases as well when the protected viewpoint is disadvantaged. This has technical reasons that we explain in the paper, but this is a clear limitation of these metrics that should be pointed out here. So to sum up the considerations that we recommend when assessing viewpoint diversity with ranking fairness metrics, first of all, it's important to decide what is the underlying aim. Is it binomial viewpoint fairness or multinomial viewpoint fairness or something else? Then how balanced is the data overall? So what's the proportion of protected viewpoints? How strong is the ranking bias? And what is the direction of ranking bias? All of these are considerations that have to be taken into account when trying to assess viewpoint diversity in this way. So as a take-home message, we find that ranking fairness metrics can be used for assessing viewpoint diversity in search results, but they have to be interpreted very carefully. There are still a lot of limitations here. So these considerations that I mentioned have to be taken into account. Quickly, some future work that we thought about. So the first one is, what is an appropriate set of viewpoint labels? We decided on a specific one here, but viewpoints could also be, for example, quantified on a continuous scale, or more or less labels. So this is something to discuss. What's an appropriate level of viewpoint diversity? So how much viewpoint diversity do we actually need? Then, of course, having these kinds of metrics allows us to now assess viewpoint diversity in real search results. This is something that we definitely plan to do. And then lastly, something that we have already done that's currently under review is to align these metric outcomes with behavioral outcomes. So to see, okay, now we have a search result list with this level of viewpoint diversity. What is now the effect that this has on the attitudes of users? Thank you very much. I'm happy to take any questions.
Thank you for this talk, Tim. Great. A very interesting topic, and actually, I don't see so many questions in the comments, but I have lots of questions. What I find really interesting is that you talk about the viewpoints, but in the presentation you never meant, like you had the example of being region or non-region. These are maybe viewpoints, but there may also be topics where there is no right or where there is actually a right or wrong. Should there also be some diversity when something's like objectively proven that it's non-existent, for instance? Did you have such considerations when doing your work, or is there some upcoming work?
Yeah, so I guess you're talking about things like climate change, where different viewpoints exist, but we have a correct way to think about it, let's say. Yeah, so this is what I meant by this second point in the future work here. What's an appropriate level of viewpoint diversity? That's not just a general consideration, I think, but it really depends on the topic. And that's something that we have definitely thought about from the beginning, but it gets into an ethical, philosophical question very quickly. So I can't say that we have concluded anything there yet.
Yeah,
it's definitely something that we will keep in mind, and we will keep working.
Yeah. I'm not expecting that every paper solves the world problem, and we would just have one paper presented. So you use synthetic data, where you could assign labels, because it's synthetic data. Do you already have some ideas how you could transfer this metric or this labeling actually to real documents, or some discussion on social media? Because I think, from my perspective, that it seems very challenging when I have a statement, whether it's -2 or -1, it's maybe very difficult to assign the correct label. And you mentioned that also in the conclusions somehow.
Yes, that's definitely, as I said, that's also something we think about. So first of all, what is an appropriate classification here? Or is classification actually what we want? Or do we want a continuous scale? And different papers, I think, approach this in different ways. What we have done for a recent study that's now under review is we crowdsourced the, so we collected annotations for search result items, and there we used the same 7-point scale. I am aware of stance classification techniques and so on, but I'm not sure they would be able to do such a detailed labeling. So that's more like pro or con. I guess these are the current options. Yeah.
Okay. We don't have so much time left, and I see other questions. But I picked this one quickly. Maybe you can answer that quickly, by Alan. Do you have any idea how this would work for more multidimensional topics? Because for veganism, I can see how you would infer an attitude, but does that work, for instance, for movies?
I'm not sure I understand the question correctly. So I'm not sure I understand what's meant by multidimensional.
Okay.
So
I also have to think about that. I read out of it is that when you just have one dimension, good, bad, or
or exciting, not exciting, and
but if there are many different topics in there, and in a movie, it could be like the actors were really good, but the story was really or opinions, and actually the story is unbelievable.
I guess so. I guess in cases like this, it's maybe not so much related to fairness anymore, but more really about diversifying. So I guess in a case like this, I would go more into really diversity metrics that also exist, that typically balance also diversity and relevance, for example, in the IR setting. And then to simply compute a distance between different movies, for example. But that's something that we also haven't tackled so far.
Maybe it's a good idea to discuss that in Gather later on in the poster session. Yeah. Okay. Thank again, Tim, for the talk and the nice answers to challenging questions. Our next speaker is Martijn Millecamp. The paper that he presents has the title, What's in a User? Towards Personalizing Transparency for Music Recommender Interfaces. Again, people don't forget to ask questions and put comments in the comment functionality. You can already ask your questions during the talk, and I will pick them up later. And Martijn, the floor is yours.
Hello, everyone. First of all, thanks for inviting me to talk in this wonderful conference. But before I start my presentation, I will first present my co-authors. So I'm Martijn Millecamp, and I work together with Nini and Professor Verbert at the Augment group at the KU Leuven. And for this paper, we had the help of Cristina from the University of British Columbia. So the start of our story is like 400 years ago, when Shakespeare asked, what's in a name? But we ask a little bit different question. So what's in a user? So we looked, and what's in a user that influences the perception of users towards transparency for music recommender interfaces. So I will follow a quite untypically structure of my presentation, because I know that these online presentations can be very hard. So I will start with what we have learned, so that at least you will pick up something from this presentation. So what we learned is that if you have people with a high domain experience or with a low domain experience, that they have a different needs. For expert users, they really like the explanations. They need that support. But for novice users, it's not so much. They need really simple explanations. If they become too complex, it becomes overwhelming. Another difference we found was with users with low and high openness. The people with low openness, surprisingly, they really want explanations. And they really feel more supported if they have explanations. But people with a high openness, yeah, they were not so convinced about the explanations. So maybe we think that they need more exploration, more explorative explanations than like the explanations that we give them. We also found different gaze patterns between different users, which means that probably gaze can be used for on-the-fly user modeling. Or maybe we can even adapt the explanations based on how users look to the explanations. So the rest of my presentation, I will first explain why we did this research, then I, of course, will explain how, and then I will again explain what the results really are. So why did we do this research? Yeah, I think maybe you have noticed that recommender systems are all over your daily life. Maybe you check Facebook to know which things that are on your wall, but also which friends you should like. LinkedIn gives you recommendations what jobs you should like. Netflix what movies, but also Spotify which music you should listen to. But maybe you have also wondered, like, how do these recommender systems work? These systems that I just mentioned, most of the time they don't explain why these different topics are explained to you. So that's something we wanted to solve. But a different thing is that all of these interfaces give like a one-size-fits-all explanation, one-size-fits-all interface. But isn't that weird that your nephew, who's maybe a DJ, and your grandpa, and they both have Spotify, but they see the same interface, even if they are completely different and they have completely different needs? So luckily, there is already some research that investigated the effects of personal characteristics. For example, this paper by Yu Cheng Yin, also from our group, checked the difference between a scatter plot and a bubble viz, and they found some differences on musical sophistication. There are also some research about how different explanations have a different effect on different users. For example, this paper of the group of Jürgen Ziegler, who found that in the camera domain, argumentation explanations are much more interesting for specific kinds of thinkers, like the rational thinkers. We also had another study in which we found, like, we investigated these personal characteristics. Do they appear in different? Do they have the same effect in different domains? And we found that there are differences between the camera domain and the music domain. But in the music domain, there was an effect. In camera domain, there wasn't. So what we really want to do is to combine these kind of researches. You want to combine these research on explanations and the research on personal characteristics to have like studies similar to this, which was also my previous study in IOI, in which we combine or in which we check what is the influence of personal characteristics on the perception of explanations. But what do we do different this time? This time we added eye tracking, because eye tracking really have the potential to find differences between different users and how they look, how they are interested in the different things. So to conclude, because there is no one-size-fits-all transparency, and it's not clear yet how to design these adaptive explanations, we added eye tracking to, and eye tracking has the potential to give insights. We added eye tracking to this previous study to investigate which personal characteristics have an influence and how these different people look to the interface. So how did we do it? So we built a recommender system on top of the Spotify API. And what this API allows is that there you can give some artists and give some audio features, and based on these artists and audio features, you get recommendations. So this was the interface, and on the upper left corner, you can see that there you could give the artists. Underneath, you can see where the preferences are. And then on the right, you see all the recommendations, but also they are explained in terms of features. and which like the features you asked and the features that this song has. So there are 3 main phases in this study. We had an initial phase in which we asked the users to fill in some demographics. We asked for the need for cognition, the musical sophistication, and the big 5 personality traits. Then we have the preparation phase, in which we needed to calibrate a Tobii 4C remote eye tracker on a 27-inch display, and this eye tracker had a 90 Hertz rate. So then the real task started. So first, to avoid the learning effect, we give some time to explore. Then we gave them the task to make a playlist, of a few songs, and then we evaluated we evaluated 2 times the interface before we get to the final phase. What we evaluated were the recommended effectiveness, the perceived novelty, the good understanding, use intention, choice satisfaction, trust, confidence, and decision support. And for the eye tracking measured, we measured the attention they have on the recommendations, both the absolute and the relative time. We also checked the gaze transition entropy, that's how fast they move around the interface. And a high amount means that they have like an equal transition to every area of interest, while a low means that they really fixate on specific areas. We have also the gaze stationary entropy. We don't look to the transitions, but we look to the fixations. And then in the final phase, we asked some questions. So we had 30 participants, and each study took like 60 minutes on average. And then it's time for the most interesting part, and that's what was the results. So one of the first things we found is that there was no effect for need for cognition, which was quite interesting to see, but we need to further investigate why this was. Then we found for openness that low openness users really liked the explanations, even if they didn't find new songs. And for high openness, we saw the opposite, that they found more songs, but that they are still not convinced about the explanations. So for musical sophistication, we found the same, that people with a low musical sophistication or with a high musical sophistication really liked the explanations. But I see them almost out of time, so I will quickly skip to what did we learn today. So what did we learn today? It's the same slide as before. If you have domain experts, they really need explanations because they feel more supported. But if they have novice users, they need more simple explanations, so make sure that they are not overwhelmed. If you know for the openness of users, please make sure that they that the explanations really support search for specific music, while for high openness users, it should support exploration. And then at last, we see different gaze patterns between different users. So that's future work for on-the-fly user modeling and adaptive explanations. So that was it for my presentations. Are there any questions?
Thank you for your talk, Martijn. Yeah, there's a question that I can read in the hidden channel. Do you plan to repeat the study in a different domain, so not for music, or is it something that is so specific to music that is actually not so transferable in your expectation? We don't know yet. Huh?
Yeah. So one of the studies we tested this between 2 domains, the camera domain and the music domain, and there we found that it was very specific to the music domain, because we think that if you go to a domain that has higher risk and that have high stakes, that your personal preference on how you interact with the interface got overridden, because the stakes are so high, you really are focused, and even if you have a low or high openness or low or high need for cognition, because there are so much at stake, you discard your personal preference and you focus on having a good result. So I think for the low stakes domain, for example, movie recommendations, I think we can see the same. But for high stake, I think there will be other personal characteristics that come in play and not these personal characteristics that I tested here.
Okay. Yeah, I'm just thinking myself if this low stake is also very present in general in entertainment, in the entertainment field or creative industries. I'm not sure, just some loud thoughts on that. There's another question in YouTube. What is meant by the finding that there is no need for cognition?
So no, there is no effect for the need for cognition. So we tested if need for cognition moderated the way users perceived the explanations, and there was no effect for need for cognition.
Could you give an example of what you mean with this cognition thing?
Yeah, so need for cognition is a psychology construct on how people prefer to think, if they prefer to put a lot of cognitive effort. And we thought that people with a low cognitive, with a low need for cognition, so that they don't prefer to have a really think about it, that they would like the explanations because it helps them to think or to make a decision without thinking, and that people with a higher need for cognition, that they would less like these explanations because they put a lot of thought in it anyway, and then these explanations don't really add so much for them. That's also what we found in our previous paper. So we expected to see the same result here, and we didn't see that. But we have a hypothesis, and I tested this hypothesis, and that's for a new paper, is that one of the things that makes difference is if these explanations are on the screen all the time, or they really need to click. So if they are on the screen itself, we don't really see a difference between low and high need for cognition. But if they really need to do effort to see these explanations, we see a difference. We see that need for cognition moderates the effect.
That's interesting. So again, high expectations for a talk next year to learn about the results on that. So thanks for your talk. Again, clapping my hands. You just hear myself clapping. Thanks for the talk. That's actually the end of this session, but only this session. So we move forward in the program. The next point in the program are posters. So poster session again. Please come to gather, and we will gather together in the poster room. Looking forward to meet one or the other in the poster